So, first of all, today is the live session for the 7th week for this particular course of fluid dynamics for astrophysics. So, as we look behind, we started with some viscosity and those things, and then we move on to the formation of shocks. And then in the last class we find out those subsonic, supersonic speeds, transonic flows, and then we discuss some application of the D level nozzle, right, which is applicable when you are launching some rocket. So today there will be some continuation of the shock jam condition in terms of some MCQs. With that, we will have some advanced topic which is more focused to the astrophysical situations like solar wind and the accretion phenomena. So I will discuss those two things one by one. So so I am Shripan. I am working as a PMRF at IIT BHU, and to conduct this type of live sessions once in a week is one of the deliverables of my PMRF scheme. So okay, let's have a look at the first question first. So this is not a MCQ at all. So explain simplest physical reasons behind transonic behavior of solar wind and spherical accretion of material to compact objects. So first of all, we need to understand, or we need to recall, that what is a transonic behavior. So we know there is subsonic, right, and there is supersonic, depending upon the velocity of the flow itself with respect to the local sound speed, right? Now transonic, what happens is, so if a flow is initially subsonic and then it is converting to a supersonic or vice versa, that will be the transonic behavior, right? So now we have two phenomena here. First one is solar wind, second one is the accretion of material to compact objects. Let us look at those one by one. So what is solar wind is say you have sun. Okay, so this is not the sun at all. Yeah, so let's say you have sun. Okay, so what happens is, in sun you will read in different I think classes, but so in sun what happens is, you have photosphere. What you see naked eye when there is no solar eclipse is the photosphere itself, and that is visible in the white light. Now there is some atmosphere of the sun, as earth has its atmosphere. Likewise sun also has its atmosphere. So in sun what happens is, there is an surprise. So if you consider sun as a black body, as you read in undergrad courses, then you expect that as you move from the core, the temperature should falls, right? Now and it is there, because at the core it is around 10 to the power 7 Kelvin, and then as you move on to the photosphere, it decreases to 5800, right? Now but the case is, if you go to the upper solar atmosphere, so as you move further from the photosphere, the temperature suddenly started to increase as you move further from the source, right? So that gives you the problem of coronal or chromospheric heating, which are the outer atmospheres of the sun. Now if the corona is very hot, so what happens is it has very high pressure, so it should not have the hydrostatic equilibrium, right? So in sun everything is compact because of the gravitational pull which is inwardly directed. Now if there is an outward pull which is greater than the inward pull, that causes the that some material can be detached from the sun, right? uh, so that can happen only if that the pressure or the temperature in the hot corona is such high that the thermal pressure or thermal movement is very much higher, so that it can be higher than the inward gravitational pull, and it can detach some material in the form of, let's say, solar wind. Solar wind is basically a flow with lots of charged particles, right? And that is due to the high thermal pressure which is greater than the inward gravitational pull. So therefore, now in the corona you have hot corona, right? So you have hot corona, and as the solar wind goes in the heliosphere, so what happens is that your energy is conserved somehow. Okay, now if energy is conserved, so we have kinetic energy. Simply there can be other forms of energy, but in the simplest physical reason you need to think about, you have kinetic energy, you have internal energy in the form of the temperature and pressure, right? Now as you are in the hot coronal region, what happens is your internal energy is quite high because your temperature is quite high, so the kinetic energy or the speed is not that much high. But as you move outward from the corona, what happens is the temperature falls off because solar wind is cooling down. So as it is fall off, so due to the energy conservation, what happens is your kinetic energy will be increasing. Now kinetic energy increase means your velocity is increasing, right? So initially the velocity is very low, and as the solar wind is moving in the heliosphere, its kinetic energy will be very high. Okay, so that means initially it is a subsonic, and then it is going to the supersonic regime. So that is the transonic behavior of solar wind. Okay, so in the solar wind case, what happens is you can write it, give insert a text box. Initially the internal energy depending upon thermal pressure is high, kinetic energy is low. As solar wind goes in the heliosphere, it cools down and its internal energy gets decreased, resulting in increment of kinetic energy. Okay, now fine. Okay, So this is the first solar wind. Now what we have is spherical accretion of material to compact objects. So what happens is, when you have a compact object, so let's say this one is a compact object, and you are this is accreting some material which are around it, right? So now the gravitational energy is given by minus gmm by r, right? Now r is the distance from this core to the material which is getting accreted, right? So as it is moving towards the compact objects, the r is getting lower, right? Now if r is getting lower, what happens is this is getting higher, so it is becoming more negative, right? So if it is getting more negative, what happens is, due to the energy conservation, if it is more negative, that means it is getting lesser, so your kinetic energy will increase, right? So again it starts from a subsonic regime and it's move on to the supersonic regime due to the conservation of energy, as the gravitational pull is getting more negative as the materials are coming towards the compact object. Okay, so yeah, now you can write it like in case of accretion, the material is moving towards the compact object, its gravitational energy get more negative, resulting in increment of kinetic energy by virtue of conservation. Okay, so this is the answer for the first question. Now the second question is, so consider the spherically symmetric solar wind type solution for transonic flows. So what happens is, so you can have this kind of a plot where you will have this m equals to 1 here, right? Or m square is going upward, or r is the distance, right? So for solar wind, what happens is, initially it is subsonic, so it will go like this. So this is your sonic point. So location of sonic point is independent of the gas temperature. Now sonic point is that for which B equals to CS, right? So it depends upon the sound speed. Now if it is depending upon the sound speed, and the sound speed itself is like a root over T, right? So if it is root over T, so what happens is, the location of sonic point depends on the gas temperature. The second one is correct. And also the dynamical equation remains same under changing the sign of gas velocity. So why? Because if you remember the dynamical equation here, just give me some second to remember it. Yeah, so the dynamical equation is like this: u minus c is squared by u, okay, and then du dr, right, equals to 2 cs square minus, sorry, there will be r, and then gm by r square, right? So see, if you change the sign of the velocity, what will happen? You have u square minus cs square, and then in denominator you have u and then du. So if you change u to minus du, that means your du is also getting changed to minus du, and square term will remain the same thing, right? So this tells you that if you change this dynamical equation remains same, right? So for this equation, sorry, for this question, your answer will be will be 2 and 3, okay. Okay, now this is the next question. So it is telling that consider the atmosphere of a spherically symmetric isolated star. The steady state momentum equation for stellar atmosphere is this one. So what you have is d p dr equals to minus gm by r square minus by r square, and then you have mp kbt, mp kt, okay. Now what else is given is t equals to t naught r naught by r 2 to the power 7, right? So another thing is t equals to t naught r naught by r 2 by 7, right? So what you can do is, what you need to do is the pressure term, right? So you have dp by p, right, equals to minus gm by r square, and then 1 by kt. So this is k t naught r naught 2 to the power 7, sorry, 2 by 7, and then here this is r 2 by 7, okay. Now if it is the case, so you will have minus gm m by k t naught r naught 2 by 7. So this much is constant. Now you have the integration. Let's say dp by p. Let's say this is p naught, this is p, and here it is, you should have a dr right here. There is a dr. So this is r2 by 7 minus 2, and dr, it should be a 0, should be your r, right? So in this way you would have GMM by KT naught R naught 2 by 7, right? So it should be written again. Two by 7, and then what happens is 2 by 7 minus 2, so it should be minus 12 by 7, right? Minus 12 by 7, so it can be minus 12 by 7 plus 1 by minus 12 by 7 plus 1. Okay, this should be 0, this should be R. So minus GM M by K T naught R naught 2 by 7, and then minus 5 by 7, so this should be a plus here, and this would be 4 by what, maybe plus, might be 7 by 5, and this should be r to the power minus 5 by 7, so 1 by the power 5 by 7. Okay, now if we look at this equations, we will get this 7 by 5, right? We could have a look at this, because this is the case. So yeah, it's like r to the power minus 5 by 7. So if you have r to the power 5 by 7, that means you should have the so this is basically you have ln p, right? So ln p minus p naught, right? So it should be ln p by p naught, so that means you have p equals to p naught exponential, right? And another thing is here, you see there should be a minus sign, might be somewhere. Okay, so I have some thing to do, that r equals to infinity. Say r equals to r naught, it should be t equals to t naught, right? It's true. And p equals to p naught. Okay, so what happens is you should have that r naught here, right? This is not 0, this should be a r naught. Just a second, this should be r naught, right? It has to be r naught. So if it is r naught, then what happens is this one is here, right? This entire thing is there, and then this is minus 1 by r naught 5 by 7, right? Okay, okay. So if this is the case, now what happens is p equals to p naught, and then in bracket what could I have is 7 g m small m by k t naught, right? r naught to the power 7. So if you have here r naught, that means you were okay, so that means you are multiplying it by r naught to the power 5 by 7. So that is like this, r by r naught, right, minus 5 by 7, and this should be a minus 1. Okay, so this will be your answer for this question. Okay, and this is your answer. So this one is your answer. Okay, so this one, format, insert. So yeah, so answer is B. And another thing is the pressure goes to 0 at an infinite distance from the sun, from the star, right? So if you give this r at as infinity, that means this is 0, right? Now still you have a exponential of minus 1, so it is not going to 0, right? Because this term is 0, this will be 0 as r tending to infinity, but you have p equals to p naught by e, which is non-zero term, right? So this is not going to 0, so this is not a correct answer. This one is also not a correct answer because this one is this thing. Now if the pressure at infinity is not equals to 0, then still atmosphere is cannot be in hydrostatic equilibrium. Okay, so this is not a correct answer. So only the answer D is your correct answer. Okay, okay. Now what you can do here is you can take a screenshot of this and a new slide in which you can put this, right? So go to there, you will get this, right? Okay, now you have this one solved. Now the next is this. Now consider spherical accretion by a compact astrophysical object. Pick the correct statements. So a radiative force due to photons increases with an increase in the Thomson scattering cross section. So first of all, let us recall the outward radial force equation, right? So that is around, if let's say outward, this is sigma T L by 4 pi r square C, right? So your sigma T is your Thomson scattering. Now if sigma T is getting increased, then F out is also getting increased. Okay. Now the Eddington accretion rate for a star with a larger radius will be smaller. Now if you remember the Eddington accretion rate formula, which is m dot equals to 4 pi then mp then c r star, right, by sigma t. Now r star is the radius of the star. So if r star is increased, then this m dot will be also increased. Okay. So Eddington accretion rate for a star with a larger radius will be larger. This one is correct, this one is correct. Okay. So insert text box. Answer is 1 3. Okay. Okay. Now the next question is, so what is the this is recording? Yes. Okay. So what is the continuity equation for a moving shock wave? So first of all, you have to understand in which frame you are considering it, right? So when you are talking about the stationary shock, that means your medium is stationary and there is no point in considering any velocity. It is stationary because it does not have any velocity at all, right? Now when you have a still from lab observer, you are saying that okay, shock has some velocity, but the medium in which shock is propagating, it is stationary. So you are saying that this is a stationary shock wave, right? Now if you are an observer who is moving with the shock itself, what she or he will see is the shock is stationary, but the medium itself has two velocities, right? Because he is moving with the shock, so he will not feel the movement of the shock. Instead, he will feel the gas behind him is moving far away. The gas ahead him is moving towards him, right? So when it is moving towards him, that means it is an upstream, and when it is going away, because we have to look at that point, so that means that is your downstream. Okay, so if this is the case, so we got that point, that rho 1 u1 equals to rho 2 u2, right? Now that is the case when your medium is stationary. Now instead, if the medium itself is moving as well as the shock wave is moving, and W is, now if you look at this explanation here, it will be clear to you that continuity equation across a shock wave is given by this formula, right? Rho 1 u1 is to rho 2 u2. Our subscripts 1 and 2 are the sections behind and ahead of the shock wave. Now the above formula is valid only for stationary wave. For a moving wave, there is an induced gas formation. Now when you have a moving wave, right, so there is an induced gas formation behind the shock wave, resulting in W minus UP being the velocity behind the shock wave, which is relative to the wave, right? and W is the velocity of the gas ahead of the shock wave, right? So instead of U1 you will have, instead of U2 you will have W minus UP, and instead of U1 you will have W. So UP is the velocity of induced mass motion due to gas, W is the velocity of the normal shock wave. So the answer here will be this one, that rho 1 W equals to rho 2 W minus UP. Okay, so keeping this in mind, that rho 1 W equals to rho 2 W minus UP, rho 1 W equals to rho 2 W minus UP, right? So now what is given? Your shock speed is given to be 900 meter per second, right? And the density ratio across the shock wave is 0.6. So this rho 1 by rho 2, which is equals to W 1 minus, right, UP by W. So rho 1 rho 2 is your 0.6, so you have UP by W equals to 1 minus 0.6, which will be 0.4, right? So UP is 0.4 into 900 meter per second. So 4 by 10, that is 2 by 5. So this should be 360 meter per second. Okay, now so should have a new slide in which we are going to have this one. Okay. Now the next question is, how is total enthalpy related in shocked and unshocked region of a stationary and moving shock wave respectively? So Bimal, are you there?
Yes, sir.
So can you answer this question, at least for the stationary shock waves, that how should the enthalpy changed for shock and unshocked region? Hello?
I'm done, sir. I'm done.
Sorry? Okay, so for stationary shock, what will happen is the enthalpy will remain constant, and when you move to the moving shock problem, it will change. Okay, so for stationary it will constant, for moving it will be changing. So the answer will be, the answer is do second one. Okay, okay. Now the next question is, pick the correct statements. Quantities with subscript 1 and 2 represent the pre-shock and post-shock values respectively. The other symbols follow the usual convention used in the course. So if you remember that when you were deriving the shock conditions, what you have is basically you have rho 1 v1 equals to rho 2 v2, which is the mass conservation equation, and then p1 plus rho 1 v1 square equals to p2 plus rho 2 v2 square, right? This is momentum conservation. And then you have another equation which is p1 v1 equals to plus rho 1 epsilon 1 plus half rho 1 v1 square v1, right? This should be equals to p2 v2 plus rho 2 epsilon 2 plus half rho 2 v2 square and then v2. Okay, so using these three equations, and with this you have to use the formula for that pressure and Cs square basically. So you can write that epsilon is basically P2, okay, epsilon is basically P by gamma minus 1 and then rho. Use this with these equations and do some algebra. You will be able to achieve this equation, which you know as the Rankine-Hugonot condition of v1 square plus gamma p1 v1 by gamma minus 1, right? Rho 1 v1 equals to half v2 square plus gamma p2 v2, right? Gamma minus 1 rho 2 and v2. Now if we know this equation, using some more algebra, you will go to the equation like p2 by p1 equals to 2 gamma m1 square minus gamma minus 1 and then gamma plus 1. Okay, so if it is the case, then what the question is asking for, basically just a minus 1 with this, right? This is basically p2 minus p1 by p1, which is these things. So if you do this, 2 gamma m1 square minus gamma minus 1 and then minus gamma plus 1 and in between gamma plus 1, right? So if it is the case, so minus 2 gamma, right? So 2 gamma m1 square minus 1 by gamma plus 1. Okay, so this is your p2 by p1 minus 1. And another thing from this 2 will be correct. I will leave it to you guys for calculate it. You can do that using these equations and some kind of algebra. Okay, now the next question is that consider an ideal monatomic gas passing through a normal shock. The upstream Mach number is 4 and the upstream velocity is twice the downstream velocity. So the downstream Mach number is, so you need to calculate the downstream Mach number here, right? So give me just a few seconds. Yeah, so using Rankine-Hugonot condition, you can before that I should have this one. So you can slide, insert. So now what happens is you have an equation which can be derived from Rankine-Hugonot condition, that m2 to the power minus 2 equals to m1 minus 2, then u1 by u2 square plus half gamma minus 1, right? And then it should be u1 by u2 square minus 1. Okay, so now we need to put this gamma equals to 5 by 3 here, and also your upstream Mach number is given by 4 and the upstream velocity is twice the downstream velocity. So what does it mean is u1 is equal to 2 u2 and m1 is 4 here. Okay, now if this is the case, so m2 minus 2 inverse m1 is this, so 1 by 16, u1 by u2 is 2 square means 4, so 1 by 4 plus half 5 by 3 minus 1, that is 2/3, right? So 4 minus 1, okay, because we were, yeah, so 2 it's cancelled out, this is just 1, so this should be 1 by 4 plus 1, so this should be 5 by 4, right? So m2 square will be 4 by 5, therefore m2 will be 2 by root over 5. Okay, so this will be your answer. Okay, yeah, so yeah, new slide, insert, Now there is another question here, is what is the temperature ratio across a moving shock wave in ambient air if the pressure ratio is 8.5. So in a moving shock wave you will find out this kind of a equation, that T2 by T1 is P2 by P1, this equation. And since this is ambient air, that means we can think of it as diatomic gas. So this is 7 by 5, which will give you 1.4, and given that P2 by P1 is 8.5, so putting in this values we will find out that T2 by T1 is 2.37. Okay, just remember this formula. It is not that much pretty straightforward to calculate it directly, so you have to remember this formula, and putting the value given in the question you can find out the temperature ratio across the moving shock wave. Okay, so yeah, I think I'm done for today. So yeah, so Bimal, any question?
No, sir.
So you understand everything?
So let me understand and expect the derivation part is covered in the last time.
Yeah, so derivation parts are a little bit, lengthy things, and it's not that much easy to derive everything in class because it takes lots
Okay.
of time.
Okay.
Yeah. So
Okay.
yeah, okay. So we will stop here today. We will meet on next Saturday for the next week's class.
Thank you.
Okay. Thank you.